So yeah, thanks a lot to the organizers for today. Yeah, my talk is a lot more theoretical than the previous ones. So yeah, let's see. But I'm going to talk about convergence control with kernel discrepancies, so maximum mean discrepancies and kernel sign discrepancies. And this is work with Lester McKay, Carl-Johan Simon Gabriel, Marjo Lamy, and Mike Betancourt. Basically, I'm going to mention a bit. We talked a lot about MMD and KSDs, but I'm going to try to introduce them in a slightly different way to kind of emphasize some of the topological aspects and geometric aspects of MMD and KSDs. And I think my goal is going to try to introduce a few key concepts which are important when you study convergence control and whether the discrepancy that you define is able to separate measures. So in particular, I'm going to try to introduce the Schwarz distribution, which is really important when you study KSD. And essentially, the first part of my talk is going to be related to these topological and geometric ideas. And the second part of the talk, I'm just going to present some results and quickly mention some applications where the relevant with time ratio gradient descent and so on. And the key idea is that the results should apply to both bounded and unbounded kernels, because there's other results about bounded kernels in the literature. But when you deal with kernel sign discrepancies, the kernels are typically unbounded. It's much harder, or the results are much weaker for these types of discrepancies. The main reference for the results, though, if you're interested, is that paper at the end. So basically, when you define a discrepancy, so some kind of thing that quantifies out to distribution rho and mu differ, you will have some requirements that your application needs the discrepancy to satisfy. And I'm going to be interested in two requirements which appear in many applications. One of them is called characteristicness, at least in the kernel literature. And basically it just says, okay, so if my distribution, if the discrepancy between my distribution is 0, this should be true if and only if the distribution are actually the same. And this seems like this is a very basic kind of requirement, and it's typically not enough. So typically you also want the next requirement in that you want MMD to be useful even when the measures rho and mu are not the same. So for example, you want that if it seems that mu or a sequence of mu is getting closer and closer to rho, you want to be able to detect that you're converging to right measures. So that you want to identify if you're at least getting close, because you will typically, in particular in the misspecified model, you will never achieve exactly the target. So the other requirement is there's many types of requirements related to that, but the one I will talk about is called control of convergence, and it basically says that if you have a sequence of distribution rho n converging to a distribution rho, and the MMD equals to 0, that should imply that rho n generally converges to the target distribution. And when I say converges, I mean in terms of weak convergence. If it's not just implied, but these things are equivalent, then this is what we call Mitchwising. So if convergence in MMD is equivalent to weak convergence, that we say that the kernel Mitchwises with convergence. Now this here, rho n and rho are kind of arbitrary, and in many applications, those related to KSD rather than just general MMD, you typically have a fixed target, and you want to kind of just fix it, and then just look at things that converges to it, or separate rho, the target, from like a class of distributions. So you have kind of like targeted version of the requirement that I mentioned before. The first one just says MMD separates my target from a given set of distribution, and it's basically the same requirement as before, except that rho is fixed. So now you want just that if mu belongs to a certain class of distribution, big mathcal M, and the MMD is 0, that should be true if and only if mu is actually the target. And when M is the Wall-Set operating measure, then we just say that MMD separates rho from all distributions, or is rho separating. And similarly, in terms of control of convergence, we say that MMD controls convergence to a given target if the following implication holds. So again, your rho is kind of like fixed before, you don't touch it during all your results, and then rho n is arbitrary. So we've introduced, I think we talked a lot about MMD, but I'd like to introduce the way I think about MMD, and the reason why I quite like it. Basically, there's two natural ways when you think about distinguishing distribution that depending on whether you're a mathematician or a physicist or statistician come to mind. Typically, if you're a physicist or statistician, you're kind of interested in testing distribution against functions. You're typically interested in something which is called the worst case integration error over a class of functions. So this is the first discrepancy, with mapcal F, where you just test the value of integral and you just output the worst case integration difference. If you're a mathematician, typically for you, distance is a well-defined concept. It means that you have some kind of like a metric space. And so typically then in that case, what you want is to have some kind of map phi, which takes your distribution, map it onto some metric space, and just compute the distance with respect to a well-defined, respectable metric. And the nice thing about MMD is that it connects, or like kernel discrepancies, that it connects these two views together. Basically, the idea is that these two notions coincide when the set of functions that you use is the unit ball of a Hilbert space, and rho and mu act continuously on that Hilbert space. So in that case, the worst case integration error over like the unit ball of a Hilbert space, because your distributions are acting continuously, the integration is equivalent to the dual norm between the restriction of the distribution to the Hilbert space. So with your distribution, they typically integrate a lot more function that are in your Hilbert space, but you can restrict them. And when you and basically the restriction to that is becomes a continuous linear functional of your Hilbert space, and you can apply the dual Hilbert space norm, which is equal to the Hilbert space norm, basically by rich representation theorem. And so what that says is basically you have an equivalence between a worst case unit-ball integration error and like a genuine metric, and in which the map phi that we have before is just a restriction. So instead of acting your measure on all bounded measurable function, you just act them on your Hilbert space. And so here we see that the key idea is continuity to have the equivalence. And now that's convenient because reproducing kernel Hilbert spaces are by definition, they're defined to be the Hilbert spaces of function such that the Dirac measure is continuous. So basically the definition of RHS is really at the heart of it is just the idea that integrating respect to a Dirac measure or just evaluating a function, that operation should be continuous. So you know that at least for Dirac measures or measure with finite support, you will be able to define, you will get that equivalence between the unit ball discrepancy and the metric distance. In fact, there's a much cooler result about RHS. It says that a measure will be continuous, will act continuously by integration over RHS if and only if your RHS consists of integrable functions, which is exactly what you would require anyway to be able to integrate the functions. So basically, that's what that says is that as long as your RHS, basically, if you have to measure rho mu, as long as you can integrate all functions in your RHS, you're able to define the MMD. And it's important because before in the previous talk, we haven't talked that much about when MMD is actually defined. But when your kernel is not bounded, MMD might not be defined for arbitrary distributions. But this theorem tells you that as long as your RHS contains integrable functions, then it is defined. It is equal to the restriction of, it is equal to the Hilbert space distance between the restriction of the measures, and you have the usual integral form on the right-hand side, which makes it also computationally kind of like tractable. And so what you will have noticed is that I've introduced maximum indiscrepancies, and I still haven't mentioned kernels. And I did that kind of on purpose, but it's actually very natural. Is because like the key idea between the maximum indiscrepancy is not a kernel, it's continuity. And in fact, this is what Fields methodist Laurent Schwartz, when he developed the theory of RHS, he has like a 160 pages paper from a Fields methodist looking at all the theoretical aspects of RHS. For most of the papers, he never actually mentioned the kernel. What he says is that, okay, there's one key thing about RHS is that they are Hilbert spaces, so H, and they are continuously embedded in a topological vector space, which is also locally convex and Hausdorff. Basically, the point is that under this simple assumption, you can derive basically every property of RHS, which people usually derive via kernel. And this is actually related to one of the things we mentioned before, one of the questions by Jeremias, in which I think Bad Redin was mentioning about embedding distribution in Hilbert spaces, which are not RKHS. And this is exactly the situation in which you realize that the mathematics is the same, even though you don't have a kernel. So when you look at score matching, you're exactly in that situation, except that instead of having a Hilbert or an RKHS, you still have a Hilbert space, and the Hilbert space is L2. And the Hilbert space still satisfies the assumption is still continuously embedded in a space of thing called like sparse distribution, which I'll mention after. And the point is that actually most of the when we work with this discrepancy, when we do a proof with score matching, and when we do a proof with like say KSD, the proof is exactly the same. When you write it mathematically, without the kernel, it's actually pretty much the exact same proof, because it only relies on this like continuous embedding. So yeah, basically, just want to mention that the key idea between the definition of maximum discrepancy is this continuous embedding. And the fact that you have a continuous embedding, so from H into this topological vector space, means that you can take its transpose, which defines a map between continuous linear functionals over H and T. So T star is a set of continuous linear functional over T, and H star is a set of continuous linear functional over H. So just the transpose of the inclusion is the restriction, which is the map I gave before. And the point is that your space T will be like a big space, like it will be a space which has like a lot of function, which like can really discriminate between the distribution between the functions that act on it, while H will be a small space. And the idea is that if your H is sufficiently big to approximate to be dense in T, which means it's able to approximate all the functions in T, then you essentially can forget about the action of functionals on T and just study the action of functional over H. So this is exactly what happened in the formula of MMD, in which you compare distribution and you just look at how they integrate one function, the kernel, and somehow that tells you a lot about how they integrate different functions. So basically here the idea is really just what happens behind the scene is that you have this continuity, which allows, and you have this denseness and continuity, which allows you to recover the integration of like many functions just from the way distribution integrate the kernel. Okay, and now the key thing is that because we have a Hilbert space, we have a nice structure, so we can measure the length of the continuous linear functional on T with respect to the Hilbert space norms. This is MMD. Now, for what we'll be interested in, or what I'm going to be interested in, we're going to be interested in separating distribution, so element of T star. And it turns out this, because of the discontinuity assumption, is completely equivalent to HK being dense in T. So it's kind of what I was mentioning before. So essentially, a lot of the proof we're doing, where we're controlling convergence, is we're just checking whether HK is dense in an appropriate topological vector space. So just making a little more concrete some topological vector space of interest. So by definition, so as I said, this also applies to score matching. So by definition, RKHS is exactly this setting in which T is the space of function from X to RD or from X to R. And in that case, the kernel X is literally just defined to be the restriction of the direct measure to HK. In that case, denseness to that space is equivalent to the kernel being strictly positive definite rather than just positive definite. When T is a space of C0, so the space of continuous function that vanish at infinity, then the dual T star is just a space of finite measure. And in that case, if your RKHS indents in that space C0, that's equivalent to saying that your MMD is able to separate all finite measures. And this is sometimes called integrally strictly positive definite. You have similar assumption, you have similar denseness in different spaces that allow you to define things like conditional positive definite kernels, which also arise in some applications. But now the key thing is that when we look at KSD, so for MMD, we're fine just embedding measures. So typically, these spaces T will just be spaces of function. But when we do KSD, the situation is much more complicated because basically KSD arises as transformation from a base kernel through a differential operator. And when we want to analyze whether KSD is able to control convergence or separate distribution, we will need to embed much more complicated functionals. So the space T and T star will be much more complicated. And in particular, when HK consists of differential Bob function, we will need to be able to embed derivatives of measures. So basically, what does it mean to differentiate a measure? So in the case of mu being the direct measure, its derivative is just the actual derivative evaluated at a point x. So the idea is that in standard calculus, you can only differentiate differentiable functions. But this is really the calculus of like the 19th century. So people like Schwarz, people like de Rham, people like Sobolev, about 100 years ago, they developed a theory, which is now called Schwarz distribution or de Rham currents, which basically tells you how to differentiate things which are not smooth. Typically, how you differentiate like a direct measure. And this is a situation in which you have, in KSD, in which you have like one measure which is smooth, so you can differentiate in a normal way. And then you have another measure, Q, the alternative, which is typically non-smooth. And you need to find a way to, be able to also differentiate that measure to be able to actually compute the KSD. So this is also done a bit behind the scene. But basically, the idea is that this calculus introduced by Schwarz about 100 years ago really allows you to meaningfully differentiate things which are not smooth. So what does it mean to have this, the score of a non-smooth measure? Well, Schwarz told you, Schwarz built a theory to do that. And this is kind of what we use behind the scene. And I just want to mention also last thing. So this is what Schwarz distribution are. They're essentially a combination of differentiation and integration without the assumption of smoothness. Instead, all the assumption of smoothness is replaced by an assumption of local integrability. So Schwarz explains you how do you differentiate things which are just locally integrable rather than actually differentiable. But there's still the same notion of differentiation. So differentiation in classical calculus just tells you, well, if I change my function a bit in a direction, the derivative is supposed to represent the first order change of that function. And there's exactly the same interpretation when you differentiate much more general objects. You just have to introduce more complicated topologies.
Different notion of weak derivative. Is it different from the notion of weak derivative?
Yeah, weak derivative is a special case. So distributional derivative is what I'm talking about. And weak derivative is when your distributional derivative is itself absolutely continuous. So, let's say you have a measure which is non-smooth, you differentiate it, you can always do that with Schwarz. When the derivative of that measure happens to be a measure which has a density with respect to Lebesgue, we call that the weak derivative. But this is much, this is a very strong, it's a much stronger assumption. So Schwarz, one of the cool things about Schwarz is you can differentiate anything as many times as you want. It's very nice. Okay, so basically, now I'm gonna briefly just talk about how we apply these kind of like ideas. But really, my main goal is just to explain you why Schwarz distribution are gonna arise in KSD. So it's gonna be a few slides after. But basically, okay, so we're trying to find whenever MMD, trying to find condition for MMD to separate measures and for MMD to control with convergence, which seem like distinct thing. But actually, we've proved a couple of years ago that these questions are like they're pretty much equivalent. So basically, in the compact case, so when your space is compact, then if your kernel is bounded, metrizing with convergence to a target is equivalent to separating measures. So these two questions that we have are actually completely equivalent in the compact case. So that's the first point. However, when your space is non-compact, say Rn, then there is a slight difference, but not that big. The idea is the reason why that happens is that when your space is not compact, you are able to construct a sequence of distributions that converge to 0 in MMD, but do not converge weakly to anything. And this happens because you're able to lose, you're somehow able to lose the probability mass of your distribution with MMD, which is something that doesn't happen with convergence. And but this only happens if your kernel is not able to separate all finite measures. So basically, the only difference between the compact and so for bounded kernels, the only difference between compact and locally compact case is just that in the first case, metrizing with convergence is equivalent to separating probability distribution, while in the second case, metrizing with convergence is equivalent to being able to separate finite measures. So finite measure can be also negative. That's the main difference with like probability distribution. So some people call them sign measures. But that's the only like non-trivial thing about the bounded case. So really the difficulty only happening in KSD or like MMD with unbounded kernels. So just to now explain how Schwarz distribution appear in KSD. So basically, we've already explained why we care about KSD. Typically, you have the expression for MMD, but this is quite a nice expression, but like it's not so easy to compute when you're unable to sample from one of the distribution. So let's say rho in our case. So in that case, you want to find a way to remove all the integration with respect to rho. Now, when your target is actually smooth, this is where standard operator come in which basically you, instead of using the integral information of rho, you just use differential information. And instead you use, so basically you use integral information for mu because you have samples, and you use differential information for rho because it's like a smooth measure. And the idea, so yeah, and basically the way you build your standard operator is just to ensure that you build a RKHS out of it, which integrates respect to the target measure to 0 respect to it. So we kind of already explained that before, so I'm quickly gonna move to the next one, which is KSD. Okay, so there is a canonical standard operator which can be constructed through many in many ways. There's many motivation for it, but basically the one you saw I think a few times already before. So the one at the top, the divergence. In my opinion, it has nothing to do with Stein. I'm not exactly actually sure why it is called a standard operator. It has a lot more to do with the Poincaré or Langevin. But this is what you call the standard operator, divergence, and you can prove that that operator automatically arises when you try to just consider which are the functions that integrate to 0 with respect to my with respect to a given smooth distribution. There's a thing called like Poincaré duality, which is a topological statement, which tells you, oh, actually this is equivalent to the function being in the image of that operator. So even if you don't introduce that operator, but you just introduce the idea of smoothness, Poincaré duality tells you integrating to 0, if there's smoothness involved, it's equivalent to being in the range of that operator. So that operator arises through Poincaré duality. It arises through many other kind of types of argument as well, like diffusion approaches and so on. But basically, once you have this operator, then what you do to build the standard RKHS is you take a base RKHS of vector valued function, you apply the standard operator, and you get another RKHS, which is called the standard RKHS. The KSD then is just defined to be the MMD with respect to that standard RKHS. And now this is the key idea. So by definition, KSD is just the MMD. So the KSD given a target rho, and you apply it to mu, this is just the MMD distance between mu and rho with respect to the Stein kernel. So this is that equation. But now this is the thing. So the next equation, so the KSD by definition is just the KP distance between mu and rho. That's in the standard RKHS. But that's equal to the Schwarz distribution length in the base RKHS. So basically the length, the distance between the embedding of two distributions in the standard RKHS is exactly the same as the length of a Schwarz distribution in the base RKHS. And that's kind of nice because you understand the base RKHS much more than the standard RKHS. So when we build a standard RKHS, we use a simple base RKHS, which we understand well. And then when we get at the end, it's not so clear because maybe we don't understand as well the target measure. There's a lot of things that can go, that we understand less in the standard RKHS situation. But this tells you, okay, these are the same thing. But I'm embedding in my base RKHS something which is more complicated. I'm no longer just embedding a measure. I'm embedding d mu, and d mu I define it just below. D mu is just the score times mu, so that's still a measure, minus the derivative of a measure, which is not necessarily smooth. So if mu was smooth, then the second term would just be the score of mu times mu, which would be a measure. It would be a non-finite measure, like signed measure, but it would still be a measure. But here the key thing is that there's a derivative of mu involved. So this is actually a Schwarz distribution. And also because there's a score, the technique that your function in RKHS will tend to grow, and the kernel will not be bounded. But yeah, so basically the key idea is now, in order to understand the property of whether KSD matrices conversion, we need to study how Schwarz distribution embeds in base RKHSs, and we can't forget about the standard RKHS. And this is basically all the results. So now the rest of the talk is just like I can present some results. I don't know how much time I have. Okay. But maybe I'll stop just now because the rest is literally just saying, okay, these are results, these are the application, blah, blah, blah. But is there any mean, I'm sure there's a lot of confusion, but like, is there any specific thing I can go over just to maybe explain a bit better? Yeah.
I had a question about the very beginning, but it's possible that I missed the key thing, where you talked about continuous, Hilbert space that is continuously embedded in, first of all, into what? What was T?
Oh, the next one. Yes.
What is T?
So, okay, if you have an RKHS, T is just a space. So that's the fifth bullet point. The definition of RKHS just says that in that case, T would just be the space of all functions with the topology of pointwise convergence.
Yeah, sure.
So,
but you start from the more general case where H is any Hilbert space.
Yeah.
What is T in that case? The continuous embedded into anything?
No, so T would be, it could also be not a space of function. So for example, in the case of score matching we're talking about before, H would be L2 in that case, but T would be a space of Schwarz distribution. So this more complicated thing that I just mentioned.
Okay, so that kind of answers my next question, which was when do we want to link from RKHS to more general just in the space and give examples from.
Yeah, so for example, in the paper we did with a fix on minimum standing discrepancy and symmetry, there was actually no difference in the theory between the KSD part and the score matching part. So then it's a question of which one, the score matching was cheaper to implement, but it required like second derivatives or like, there were other issues with it. But like, my point is that when it came to just deciding, is score matching, does score matching distinguishing between distribution or on the what assumption does it do that? It actually didn't matter whether I was doing the theory for KSD or for score matching. I think that's kind of the idea. It doesn't mean they're the same thing. It just means that they have so much mathematical structure in common that often, so people typically when they think about KSD MMD, it's kernel. I think all the talk we had today that I heard, it was like you have a kernel which gives you MMD, which is fine. But when you do, I think there's a lot of time when you do the theory of MMD, when you realize that actually I can ignore the kernel. And when I do that, that allows me to understand better the relation between MMD and other types of, other F divergences and so on. So I think that's kind of like what I wanted, even in the talk we had before when he was trying to kind of explain how you can recover other methods. I think a lot of time you realize, okay, if I ignore the kernel, my proof is shorter, and it applies to more things which are different from. But there's still the kernel in many ways. So in the paper of Schwarz, in which he really goes deeply into the theory, there's I think 70 pages in which he never mentions kernel. And then he says, okay, now let's talk about kernel. And then the idea of the kernel really comes from the name. Kernel means like it's a summary of a space, it's a summary of something. So the thing about the kernel is that if my kernel is bounded, I know every function in my RKHS is bounded. So it's kind of like a way to, it's a very nice subject that allows you to summarize kind of, okay, it's differentiable, which means all my functions in RKHS are differentiable. So it's very useful, but not always. So yeah. Is there an, yeah.
Yeah, so I'm wondering, given this way of mapping, I guess the embedding space of the choice set, the set of measures set, are there nice examples when you can see even a map, I guess, particular geometric property of H to the kind of measures that you
Yes, so actually that's more in the results, but like there are basically when we actually start to do proof things about when we start to really go into what exact assumption I need for KZ separating, then it's all about understanding it's all about using exactly this kind of like differential information that you have. So for example, okay, so I'm going to give one example and then let's see if that answer is an example that actually answers this question. But like, so now I mentioned you can answer the question of whether a KSD separate measure to whether a MMD separates Schwarz distributions. So this is what I said for the moment. So in this example here, what we did was, let's say now that you add the assumption that your alternative measure mu, so now the target, can integrate the score of the target. So this is a differential, it's an integral geometric assumption. And what it tells you is that in that case, the Schwarz distribution d mu I mentioned before is a finite measure minus the derivative of a finite measure, because the fact that mu can integrate SP means that SP mu is a finite measure. Now, because you know that, it tells you that d mu lives, so this Schwarz distribution lives in a very particular space that Schwarz developed in his theory distribution book, which is called like D1L1. And the key thing is that now you know that, okay, so now I know my Schwarz distribution. I understand it very well because I know exactly where it belongs, and it's a well-studied space in geometry. And what Schwarz tells you is that in order for you to be able to separate this kind of Schwarz distribution, it's sufficient for your RKHS to be dense in a space called C1. It's the space of C1 functions, so continuously differential function, which are bounded with bounded derivatives, with bounded derivative, with a topology called a strict topology. So that's actually a quite hard topology. But the cool thing is that then the problem is solved because Schwarz tells you, okay, what do I need to be dense in that space? And basically then we have this result that tells you, okay, so just assume that mu can intrude the score. So then we know dB belongs to that space. Then we know that if you can separate those things, then your standard RKHS will separate rho from the space of all distribution that can intrude the score. And from the result that Schwarz, we know that, okay, this assumption, which seems very complicated, is actually satisfied by all kernels, like all standard kernels. So I gave a list here, but basically all the standard-based kernels that use in practice satisfy this assumption. Yeah, is that, this is a type of assumption. In another type of application, we replace this integral assumption by a group assumption. And then that gives you different types of differential geometric information. So now D1L1, that space here is no longer useful, but you can modify it you can kind of like transform it and still preserve the property that you need. And then you're able to achieve different types of results. Yeah. So you're able, basically writing things in this geometric form really allows you to then use whatever differential integral information you have and derive a result with like a more specific kind of like type of assumption. So for example, in that case, like one of the consequences of this kind of result I just mentioned goes to goodness of fit testing. So in goodness of fit testing, you have like, say, a Markov chain that target like some distribution mu, and then you just want to check whether mu and the target are the same distribution. And it has been known for a while, experimentally, that these goodness of fit test statistics work quite well. I mean, they consistently reject equality when the KSD is bigger than 0. However, all the results that you had before made much stronger assumption on the requirement for KSD to have in order for this result to be true. And the result, so for example, either they assumed that the measure mu were themselves smooths, which we don't because now we are able to differentiate non-smooth measures, or they assume that the target measure had some very strong tail assumptions. But the result I mentioned before basically just removes a lot of, basically it's much more general than what we had before, but actually the proof is like, I think it's like 2 or 3 lines. It's really just Schwarz page or something like done. Okay, so I don't know, is there any, when there's 5 minutes, I'll finish with my last application, but is there any other question? Okay, so basically then I'll just finish by just explaining then how we apply this theory more concretely. So basically the idea is that when you want to, I mentioned before that the question of whether you separate measure and when you control convergence, they were equivalent in the bounded case. In the unbound, they were equivalent in the compact case, and they were a bit more complex in the non-compact case. We have derived a result that really shows kind of exactly what's happening. Basically, what's happening is that what we've shown is that the exact equivalence is as follows. So whether you're whether your kernel is able to separate all distribution is equivalent to basically this equivalence between MMD convergence and weak convergence. So basically, here for the moment, just assume that this is weak convergence on the left-hand side. And then on the right-hand side, ignore this term, which doesn't happen in the bounded case, but you see that you need on the right-hand side, MMD, convergence and tightness. So basically, the question of whether you separate distribution, if you can prove that, this is equivalent to showing that weak convergence is equivalent to MD convergence plus tightness. So what we did in order to prove that our cases do control convergence is we separated. So first we've shown that they were separating, and that allows you to tell us that if a sequence is tight and converges to MD, then it converges weakly. And then we separately proved that our kernel enforced tightness. So basically that A implies B. And in that case, you really do have the equivalence between matrixing with convergence and separation. So basically all our results are built that way. We first show separation, which gives us equivalence between weak convergence and tight MMD convergence. And then we show separately what does it take for a kernel to enforce tightness. So basically for A to imply B.
What is the tight sequence?
So a tight sequence, so it's a topological kind of property. What it says is that if I take a sequence, so it's just like a set of measures, then there will always be a converging subsequence. So it's not basically it's something which is annoying because it's something you have to make sure you're control this is what ensures that the from Cauchy. Yeah. I mean Cauchy sequences appear everywhere, so I'm sure they appear somewhere, but it's just it's a relative compactness statement, like in terms of topology, like a pre-compactness statement. So basically, when you in terms of Cauchy, I guess if you have such a sequence, I think you can show there's a Cauchy subsequence, but then the question is whether that Cauchy subsequence has a limit within the right space. And yeah, if you don't enforce tightness, you can be in a situation that I mentioned before, in which you have a sequence of property measure that converges to zero, even though all property measures have mass 1 and 0 has mass 0, so you're losing mass during MMD convergence. So basically, tightness is just something. What happens in practice is that you build a kernel which has one part that controls tightness and one part that controls denseness, and this is how kind of you achieve proper like convergence control. So basically now I have 3 minutes. I'm just going to mention so here I mentioned one result of goodness of fit, but I think one really cool result related to the talk before is about time variation gradient descent. So so if you go to the paper, you will see you will see quite a few results about controlling tight convergence. And then the way we move from tight convergence, the way we enforce tightness is by introducing this property called like row dominating integrators. So basically, in the previous KSD literature, you will, whenever you wanted to enforce tightness to ensure that you don't have mass escaping, people would use things like called coercive functions. Coercive functions are basically function growing your RKHS, and having such a function kind of ensures that your distribution are not losing mass on the way. Now, the problem is that if you have a growing function, that means that your RKHS has a growing function, so it's not bounded. And this is kind of like one of the difficulty with standard RKHS is that when you want to implement standard variational gradient descent, the actual requirement that you need for your algorithm to be well defined is that your kernel control convergence, but is also bounded. And there's never been any example of Stein kernel which is both bounded and control convergent, because, well, first, yeah, basically typically what happens with the Stein kernel is that either they decay a bit, and if Stein RKHS decay a bit, you can never control convergence. But that's quite, yeah, it's quite rare that they decay. And if they grow, they're definitely not bounded. So if you want standard variational gradient descent, which is applied a lot, to be actually to satisfy its own requirements, you need to find somehow a standard KHS which does not decay and does not grow. And in particular, you cannot use the standard coercive function assumption. So in our paper, we've introduced this other way to enforce tightness, which is like this really unintuitive kind of definition. I mean, basically the point is that this is just what you end up showing in the previous paper using coerciveness. And it turns out that you can prove it even for bounded RKHS. So the reason why we introduced basically this definition is that then we were able to construct what seems to be the first example of standard RKHS, which is bounded and control convergence. And in particular, does satisfy the assumption of standard variational gradient descent. So again, I mean, the statement is a bit long, but basically what I wanted to go on was this particular construction here. So you see the way we build our base RKHS is by first constructing a kernel K, which is dense in C10. And that's being dense ensure that this part of the RKHS, this part of the kernel is contains enough function to be able to separate the Schwarz distribution I mentioned before. And then you have another part of the kernel, xi, yi, which essentially ensure that we satisfy this dominating indicator condition that I mentioned before. And then you have this other term A, which just ensure that you're not growing or not decaying. You're like, your standard KHS is exactly at the right level of like boundedness. And basically by doing that, so here we have a family of, basically this result gives you a family of Stein kernels, which measures with convergence. So, and as I mentioned before, this is the kind of the first time we're able to derive a kernel that satisfies the assumption of SVGD. But yeah, So yeah, this is the last thing I wanted to mention in terms of results. I think the results are much more hard to state, and I don't know which exact results you're interested in, but like, hopefully you've understand why these Schwarz distribution are important for analysis of KSD, which was my goal. So yeah, finish here. I have 0 seconds. So yeah.
Any questions?
That slide on the bottom is
Yeah.
Is that related to
So sorry, is this condition equivalent to, is that?
Because the construction is very similar, relevant to Levy-Prokhorov metric.
The Levy-Prokhorov metric?
Yeah, which is a metric for three metrics. Basically, construction based on instead of taking set as
So you're saying the Levy-Prokhorov metric is an interoperability metric which has function built on function of a similar form? I don't remember. Sorry, I don't remember the definition of the Levy-Prokhorov metric, but I would be surprised if it's that related to this definition, because this definition is really like very, very hard to interpret. It's really something that we kind of like had to somehow construct to be able to build our bounded standard KHS and show it had the same effect as a cursive function, but without being unbounded. So yeah, but either way, I don't remember the type of function that entered it. But yeah, I think this is a very odd. I mean, it's actually not so easy to build kind of function that satisfies this property. So it took us a lot of work. So I would be surprised if there's an IPM built on these kind of functions.
It's not like
Okay, it's not that name. So yeah. What's the? Okay, yeah, no, okay.
More questions? Quick question for either the last slide or one of the
related to, yeah.
You mentioned that A controls, what is it control again?
So A is basically just some growth function, growth or decay function that we just use to ensure that the Stein kernel is not decaying and not growing. It's essentially not just in terms of function. So the function your KHS or even the Stein kernel is bounded. It's bounded but not decaying.
Okay.
Because if it decays, you know for a fact it won't control convergence. So yeah, you need it to have the right dissipation level. Okay. So this is just to adjust for that.
And that line 4K C10, is that the restriction of A that A needs to satisfy, or
C10 dense?
Yeah, I was going to go to ask how do we pick A, and now I'm concerned that the answer is on the slide.
Oh no, yeah. It's just the way you pick A is you want A, so it's based on a result that I didn't mention, but you want A to be differentiable, strictly positive, and you want its derivative to be bounded. So essentially just, you could choose a different function, but the idea is just you want a class of function in which you know the decay and you know the decay of the derivative. This is basically all you need. And this class of function is, this type of A specifically that I mentioned here is a standard type of function to do that. So when you look at things called like rapidly decaying function or like slowly growing function, it's always based on how the function divided this function or multiplied this function is growing.
Yeah. Any more questions for? Yeah.
So the reason you had like the linear side y,
Yeah.
so that is the function that just grow linearly or in the edges, and then this is enough to weak over.
So basically, if you didn't have the xi, yi, you would be in the previous case in which you only control tight convergence. And the xi, yi is to ensure that whenever you converge in MMD, so whenever you have a sequence of distribution converged in MMD, then that sequence must be tight. So it's a way to enforce tightness. So if you didn't have that term, you would not do that. And if you didn't have the first term, you will not control tight convergence at all. If you didn't have the K term, no, the last one, you would not control. So yeah, this is how you build it. And if you wanted to control functions which are not bounded, for example, the variance, then you would have to add a third term. Basically, if I go back to this result, so there's three things. The term K, the last term, controls A. So ensures that A and weak convergence are related. The term xi, yi controls tightness. And if you wanted to control variance or something like that, then you would need to have another term which ensures you're uniformly integrating the kernel. Yeah.
Cool. Let's think of the final ones here.